Okay, I'm going to go through this 1987 rotation problem. This problem encompasses different concepts such as your momentum, and it's a nice energy problem. So I'm going to go through this. You have this 1 kilogram object that collides with this rod that's fixed at this axle right here. Um, when the collision happens, the object goes down this way at some angle, and the rod swings up. Okay, and at this point, it's at rest. Okay, so the first, so I assume that you read this problem already. The first question it says is determine the angular velocity of the bar immediately after the collision. So we're focused on the bar itself, not the object. Okay. So this is an energy problem. And at this point, right after the collision, this bar now has rotational kinetic energy. Okay. When it goes up to the highest point, it's at rest and it has gravitational potential energy. Now, it's important to understand that you only have kinetic energy, rotational, and not translational, because the bar itself is not translating through space. Now, if the bar was if this was the bar and it was moving this way, that'd be a different story. But the fact that it's fixed right here and the axle isn't moving, that ensures us to only have that kinetic energy rotation. Okay, so that basically is my LOL diagram. So I have kinetic energy, rotational in the beginning, and then I have gravitational potential energy in the end. So I'm going to do part A over here. Kinetic energy rotational initial equals UG. Okay, so I'm going to erase this. The equation for rotational kinetic energy is 1/2 I omega squared and my mgh. Okay, so at this point, you would go look at what the moment of inertia is for a uniform bar. And you're going to research that in your notes somewhere, and you're going to find that it's 1/3 ml squared. Okay, I'm going to bring down the omega squared, mgh. And we got to make sure we don't get confused with our m's. In one of your problems, some of you mixed up all your m's. So we got to make sure we keep this consistent. So this is the rod I'm talking about, and this is the rod I'm talking about. Actually, that is good for me because my masses can just cancel. Okay, so what is the H? Now, the rod goes from this point all the way up to this point, right? And that length of the rod is 1.2. But when we think about this, we want to think about where the center of mass is. So the center of mass is right at the center, because it's the uniform rod. And that distance that center travels goes from this point to the top. So that's my H, which is half of the distance of the length of the rod. So I'm going to just rewrite some of this down here. I have my 1/2, 1/3 L squared omega squared G. And for H, I'm writing L over 2. Okay, I'm going to cancel as much as I can out at this point. So one of my L's cancels. My 2's, my 1/2's cancel. So what I'm left with is 1/3 L omega squared equals G. I'm going to solve for omega, which is what I'm looking for. Multiply each side by 3, divide each side by L. So omega equals 3G over L. And in the 80s, when this test was given, they used a lot of numbers instead of variables. And so we're going to take the values that they gave us and plug it in this case. In 2020, I highly doubt they're going to give you numbers in a free response question like this. So I'm just going to plug this into my calculator. And I get 4.95 radians per second. Okay. For part B, thanks, babe. Okay. Close the door. Okay. Okay. So my son just brought me my water bottle in case I got thirsty, in case you were wondering what just happened. Okay. So for part B, determine the speed v of the 1 kilogram object immediately after the collision. Okay, so now I have an energy problem. And if you remember in the beginning of the problem, it said kinetic energy is conserved. Okay, so what type of kinetic energy do I have? So I want to make a new LOL diagram. And in this case, this is like where it comes into play, this O. We oftentimes ignore the O because it's very obvious what's in the system. In this case, we really need to write what's in the system, I feel. So I have the object, which is the 1 kilogram thing. I have the bar or the rod. And I also have Earth, but Earth is not really relevant because that doesn't provide any kinetic energy. Okay, so what I have here, this is immediately after the collision. So at this point, this is like right here at this point. So there's no new gravitational potential energy anyway, if you wanted to include Earth or not. So we're really focused on the kinetic energy right after the collision. So in the beginning, you have kinetic energy translational of the object and nothing else because the rod is at rest. So that is the total. Okay. Then after the collision, the object moves at some angle right there. So I have some of that. And then the rod itself is rotating upward. And there's no work done, so my totals are the same. Okay, so kinetic energy T equals kinetic energy T final plus kinetic energy rotation final. And again, this is, I want to be clear, this is immediately after the collision. Okay, so this equation is 1/2. My mass is 1 kilogram. My velocity they gave me is 10 meters per second squared equals 1/2 m. This is the 1 kilogram object still. And my velocity is what I'm looking for. That's v squared plus 1/2 I omega squared. Okay, so we're going to do a side note here. I is equal to ml squared over 3. That's 3 kilograms. It's the bar. The length is 1.2 meters squared over 3. My 3's cancel. So 1.2 squared is 1.44. That's my moment of inertia. Okay, my omega, I found it right here. So I'm going to plug that in right here. I'm going to do all my math, and I'm going to get for V, let's see, I'm going to get 8 meters per second. Okay, so for C, it says determine the magnitude of angular momentum of the object about the pivot just before the collision. Okay, so I'm looking for angular momentum about the pivot just before the collision of the 1 kilogram object. Okay, so angular momentum equations can include, I have this option, mvr, or I omega. Okay, if I'm talking about this object, I'm going to use mvr because I mean, I'm not really concerned about the moment of inertia of that and the angular speed, especially because this is before the collision. So I'm going to use this. Okay, so that's 1 kilogram times the 10 meters per second times the R, which is 1.2 meters. And it's easy mental math. I get 12 kilograms meters squared. Oh no, meters per second, meters squared. So I gave you the wrong units here. Kilograms meters squared over seconds. Okay. And then finally for part D, this is part C. For part D, it says determine the angle theta. Okay, the way I'm going to do that is, even though it says linear momentum is not conserved, angular momentum is, because there's nothing that's causing a net torque on this system. Okay, so if I know the initial angular momentum equals the final angular momentum, I need to figure out what that is. So I just solve for this. It's 12. And then I have two objects in this system. I have my 1 kilogram thing, which is going this way. And then I have my rod, which is going this way. So I'm going to say L final of the rod plus L final of the object. And I'm looking for angle theta. Okay. So this, I'm going to use I omega. So the I solved for and I lost it. Okay. It was 3 times 1. Oh, it's 1.44. Okay. So the I of the rod is 1.44. The omega of the rod was 4.95. Okay. And then the angular momentum of the object after, well, that's the MVR equation. MVR. And remember, that velocity we found, it's got to be a perpendicular. So it's got to be a perpendicular component of that velocity. So that means I'm really focused on this component of velocity. So if this was V, this would be V cosine theta, okay? Because my angle is right here, and this is the adjacent side, okay? So I'm gonna rewrite this. 12 equals, and I'm just gonna solve for this 1.44 times 4.95 is 7.128 plus the mass. That's the 1 kilogram mass. The velocity of the object I found in part B was 8 meters per second, and that's cosine theta at this point. And my R is the distance from the pivot, because they say about the pivot right here. So it's 1.2. So I'm going to solve. I want to do this 12 minus my answer divided by 8 divided by 1.2. So I get cosine theta equals 0.5075. And I'm going to plug this in, inverse answer, and I get 59.5 degrees, which is your answer. Okay, again, this is a really nice problem. This is like very numbers based, which you will not see, but I wanted you to see what this type of problem would look like with all the angular momentum stuff. And then also, it's a really nice problem because you have this rod rotating, and I just wanted to address that it only has rotational kinetic energy, not translational for the rod. Okay, have a good weekend. Bye.